Two related quantities, part one. That was awful dramatic. Let's see, we're going to use equations and graphs to describe relationships with ratios. So, our ICANs are I can create tables and graphs that show the relationship between two amounts in a given ratio. And I can write an equation with variables that shows a relationship between two amounts in a given ratio. So make sure you have today's date, your ICANs, page number, ready to move on. Which one would you choose? So I want you to think about these real quick. Which one of these would you choose? A 5-pound jug of honey for $15.35, or 3 1 5/10 or 1.5-pound jars of honey for $13.05. So, talked about this before. Just because you have a bigger thing with a certain price on it doesn't mean that that's actually a better value. But sometimes when you see something that looks like it might be a better value, it may not necessarily. So how can we figure this out? Well, we can divide each one out and figure out by the pound which one's closer. Let me use the InstiSolve process. Yes, InstiSolve, when you don't have students sitting in front of you and you can just show the work quickly. So when you divide this out, you find out that for the large jar, it's $3.07 per pound. Okay. So is that going to be more per pound or less than this per pound? InstiSolve. I should point out with this InstiSolve, it was 4 5/10 when you add those together. And I multiplied both parts by 100 because I find it easier to divide with whole numbers here than not. So anyway, when I divided that out, I actually got $2.90 per pound. So even though this larger bottle seems like, or this larger jug is going to be a better value than the jars, it actually is a better value to go with the jars instead. And this is something that some stores, like if you pay attention to the tags at like Walmart and I think even Food Lion does it, if you look at the tags on the shelves, it'll sometimes tell you the price per ounce. And so then you can make better informed decisions. Sometimes it won't have it, and sometimes you have to do the math yourself. No! Yes, math. Yeah, moving on. The painting a set. So we talked about a dependent variable before. So a dependent variable is the result of your calculation. So if a if a bolt is traveling 25 miles an hour, you need to duck. If a boat travels at a constant speed of 25 miles per hour, the equation is going to be the distance is equal to 25 times the time, right? So in 1 hour, it's going to go 25 miles. In 2 hours, the dependent variable is going to be, the thing that changes as a result. So there we go, 50. So distance here is our dependent variable. And then remember, an independent variable is that thing that is not going to change, or that's going to change, but it's the thing that's going to make everything else happen. So in this situation, time is our independent variable because time doesn't care. Time is still going to be just the time, but in this situation, for us to figure out our distance, we need to know how much time we've gone to multiply it by the 25 miles per hour to get us our distance. So distance is the dependent variable in this situation, and time in this situation is the independent variable. All right, so you're going to need to jot down this table because it's going to come important later on for some other pieces. Okay, so we need to complete this table. Lynn needs to mix a specific shade of orange for the school play. The color uses 3 parts yellow, for every 2 parts red. So we're going to complete this, try and fill in the missing blanks. So what's the total cups here? Yeah, 5, right? What about here? Well, it's 3 yellow for every 2 red. So if we use 6, that's 3 groups of 2. I need 3 groups of 3 here, giving me 9, which gives me 15 here. I think I might see a pattern. All right, so if we've got 20 total, what are going to be the 2 parts that make up here? Yeah, going to be 8 and 12, right? How do I know? Well, it took me, I need, for every 2 red, I've got 3 yellow, right? Which gives me a total of 5. Well, if I'm going from 5 to 20, I'm just multiplying by 4, right? So if I multiply by 4, I multiply by 4. What about here? To go from 3 to 18 is multiplying by 6. So I'm going to have 12. And I'm going to have 30 here. What about here? Yep, 7. And see how by using that same 7 across here for each one, I'm just moving everyone up by that pattern. So what goes on this one, since this is 16? Yeah, if this is 16, then this has to be 24, right? Because 2 times 8 gets us 16, so 3 times 8 gets us 24, which gives us a total of 40, because 8 times 5 would give us 40. Yeah, this one's easy, right? If that's 50, that's 10 times, right? So I need 30 here and 20 here. And what about this final one? Yeah, this one gets a little bit trickier because this is much bigger, but if you take 42 and you divide it by 3, you get 14. So you get 28 here, and you get 70 here. Okay, make sure you've got this down and you got it correct because it'll help us with the next part. I can't show it all on the same screen at the same time. All right. So Lynn notices that the color of the cups of red paint is always 2/5 the number of total cups. She writes the equation R equals 2/5 T to describe the relationship. Which is the independent variable and which is the dependent variable? So the independent variable is the total in this situation because it's what's getting multiplied. The dependent variable, so that's the dependent variable, is the cups of red paint, because to make that total cups, we need 2/5 of whatever the total cups is to give us whatever our red paint is needed for it. Okay, so in this situation, the independent variable is the total cups and the dependent is the red cups. Write an equation that describes the relationship between R and Y, where Y is the independent variable. Okay, probably something like this. So if Y is the independent variable, we have to take it and multiply it by something to get us to R, right? Well, for every 2 cups of red, we need 3 cups of yellow. So if we use 2/3 yellow, that'll give us our red. Think about what we did on those previous ones, like where we had 12 cups, no, I'm sorry, 18 cups given to us in yellow. 2/3 of 18 is 12, right? 2 times 18 is 36. 36 divided by 3 is 12. And we needed 12 cups of red paint. What about if we do the opposite, where R is the independent variable? Well, can't we use this, what we used before, to help us? Yeah. What are you going to put? It's going to be 3/2, right? Because for every 2 cups of red, we have 3 yellow. We can think back to where we had 16 cups of red trying to figure out the yellow. 16, if we take that 3/2 times the 16, because we knew we had 16 cups of red, I can cross cancel and divide out a 2 here, getting 1, getting an 8 here, and that gives me 24 cups of yellow, which is what we put back on that chart, remember? Okay, well, rewind back if you didn't. Okay, moving on. So, way back when we were talking about the independent and dependent variable, where we had our dependent variable was along the side here, right? So however much we changed with our dependent or our independent, we went our independent or our dependent. So let's look here. Knowing it's 3 cups yellow to 2 cups red, if we talk about that previous one that we just did, we can have R equal to 3/2 of the Y. What's it here if the Y is a dependent? Yeah, we just said 2/3. Oops. I did that backwards. I did that backwards. I caught it, so you don't need to tell me. But you still can anyway. And we're back. So the red's the dependent variable here, and we've got 2/3 of whatever the yellow is here. So if that's true, we're talking about here with the red, for every 2, we're going to get 3 cups of yellow. So it's just going to progress along like so. So in this situation, we actually do have the Y yellow being for the Y-axis. Remember that the vertical, the up and down, is the Y-axis, and this is the X-axis going across. We'll get to that eventually. But you can plot that all the way up based on that pattern. What about here? Yeah, the pattern's similar, except that since the red is our dependent variable, and we're looking at it on the y-axis, the yellow on the x-axis, it's going to make it look like so. These lines are the same, and if I would rotate this picture around, the graphs around, they would line up the same, but they look different because on here we're talking about for every 2 red we've got 3 yellow. Here we're talking about for every 2 yellow we've got 3 red. So it's just looking at it in a different angle. So why was it possible to write 2 equations for the same situation? Well, it was because we were looking at one compared to the other. So when we thought about the one as our independent variable, the other one became the dependent and vice versa. What'd you notice about the numbers that you multiply by the independent variable in each equation? Yeah. So the independent variable stayed, whatever it was in the situation. You ended up changing the other part based on what happened with taking that independent variable times whatever the coefficient was in that situation. Could we have written other equations about the situation? Sure. And we talked about the similarities between the two graphs in that they both make straight lines, and that if we rotated them around to line up, we would get the same line. But they look different because on one we were going up 3 and over 2 every time, whereas the other one we were going over 3 and up only 2. So it had a closer to flat line to it. All right, let's get wrapping up because we're over that 15 mark. So we revisited equivalent ratios by writing equations that represent equivalent ratios and graphing them. We talked about equations and relationships between like cups of red and the cups of yellow paint. How are they the same and how are they different? So the equation used the same letters and numbers, but just different ways. In one, we had 3 halves, whereas in the other one, when we were talking about, yellow as the independent variable and going to red as the dependent, we had to use 2/3 to still make it work correctly. Dependent, I hope you know by now, is the one that you find, whereas independent is the one that you're using. So like we talked about, the total or the speed. If we know that the speed was 25 miles per hour, independent variable was the time, and then the dependent was talking about how far they went in the distance. How do you know which quantity to choose as the independent variable when you write an equation, describe a situation? Well, it really just kind of depends. Remember that the dependent variable is the one that you're solving for. So in some cases, you need to use the independent variable that's there so you can find the dependent variable. In other situations, you may have all of those things, and it just depends on which way you're looking at it. All right, so we talked about equivalent ratios. We talked about double number lines and tables. How do graphs and equations help you with equivalent ratios? And how do they help you with your problem solving? So again, all of these things, the double number lines, the tables, the graphs, the equations we were just doing, those should help you to see that ratios are, can change numbers based on using them correctly. When we're talking about using 3 halves to multiply with the number of red cups, that would give us the yellow cups of paint because it was a 3-to-2 ratio, or a 2-to-3 ratio. When we were going the other way, 3-to-2 ratio. For every 3 yellow, there was 2 red. When you went the other way, it still worked out the same. It's just like we talked about with ratios before, just turning them back and forth. Again, all of those are just tools to help you solve. And I know this went super long, but there was so much to talk in here. Hey, thanks for watching.